Okay, this is lesson 4B, and lesson 4B is all about probability. So, probability is just a ratio or fraction, and here is the description of that ratio or fraction. You might want to memorize this. The number of successful outcomes compared to the total number of outcomes that are possible. Now, in probability, sometimes we talk about theoretical or experimental probability. For this lesson, we're going to be focusing on theoretical probability, but just so you know the difference, experimental probability is taking the result of your experiment. So if you take the results of your experiments and you count the number of times that you were successful in the experiment, like whatever it is you wanted to have happen, flipping a coin, rolling a die, whatever it is, then divide that by the total number of trials for the experiment. Okay? But theoretical probability is still that ratio that we described earlier. This is the one we're going to be using right here. The number of successful outcomes over the total number of possible outcomes. Okay? Now, in the experimental probability, when it says an event occurs, that means like the event that you're counting as a success. Okay? So, if you toss a coin 10 times and it comes up heads only 3 times and tails 7 times, the experimental probability of getting heads is 3 out of 10. Experimental probability of getting tails is 7 out of 10. But theoretically, there's only 1 head on the coin and 2 sides, so the theoretical probability is still 1 out of 2. Same for tails. So if you do that experiment and you flip a coin no matter how many times and whatever it comes up and you count those, the theoretical probability is still 1/2. The experiment has no bearing as long as it's a fair coin. Okay, so when we talk about something happening, like we mentioned heads and tails there. Remember how in experimental probability, the probability of heads was 3 out of 10, the probability of tails was 7 out of 10. Did you notice that they all add up to 1? Because 3 out of 10 plus 7 out of 10 is 1. If we did that in percent, then the 3 out of 10 is 30%. 7 out of 10 is 70%. And those add up to 100%. So all the possible outcomes that are possible, if you add up those probabilities, should add up to 100%. So those are called complementary events. So if the probability that it will rain today is 35%, what is the probability that it will not rain? Well, those are the only 2 things that can happen. It will either rain or not rain. So that should take care of all the possible outcomes. They should add up to 100%. So that means we can find the probability that it will not rain by taking 100% minus 35%. So that should be about 65%. If the probability of winning a game in dice is 22%, then what is the probability of losing that game? Well, there's really only 2 things that can happen when you play a game of dice. You either win or you lose. So if the probability of winning is 22%, the probability of losing would be 100 minus 22%. I should put my percent signs on there. And that would be 78%. So when you look at it that way, I'm not sure I want to play a game where the probability of losing is 78%. Okay. Now, for finding the probability of single events is pretty easy because all I have to do is count what can happen. Count how many possible outcomes there would be. Count how many ways there are to win. Okay, it's not always that simple, but it's really all about counting. For multiple events, it's a little bit more difficult. Okay, so consider this. If you flip 2 coins, what is the probability of flipping 2 coins and having both coins land heads up? Well, to count all the outcomes, there's like 3 ways that we typically do that. Well, actually 4. But let's take a look at some of those. One thing you can do is make a list of all the things that could happen. For 2 coins, you could flip them and they could become heads and heads, or heads and tails, or tails and heads, or tails and tails. And you'll see that there's 1, 2, 3, 4 possible outcomes. And if you're trying to find the probability that will be heads, then you could just count, well, there's 1 of those out of 4, so that would be 1 out of 4. You could also make a table. You could make a table with the first coin along one side of the rectangular table, and this second coin along the other side of the rectangular table. You wouldn't want to make them on opposite side to the rectangle. That would be a little difficult to make a table out of. And then you could match up the outcomes so that you have them like this. The heads matches with heads to give you heads, heads. Heads matches with tails to give you heads, tails, and so on, until you have listed all of the possible outcomes in your table, and then you could just count. Okay, well, there's 1, 2, 3, 4 possible outcomes in the table. Only one of them is heads and heads, so that would be 1 out of 4. And making a tree diagram is the third way of writing out the possible outcomes. So a tree diagram is where you take the outcomes for one event and you branch off to find out, okay, if this happens, then what could happen with the second coin? So if heads happens on the first coin, what could happen on the second coin? Well, it can be heads or tails. So we branch off to make those heads or tails. Okay? Well, what if the first coin is tails? What could happen with the second coin? Well, then we branch off to find out that the second coin could either be heads or tails. So the total outcomes, like this, it's kind of like making a list because you match them up. Heads and heads, heads then tails, tails then heads, and tails then tails. And there's your 4 possible outcomes, and only one of them is heads then heads. So the probability of heads then heads is 1 out of 4. Notice how we're writing that probability. Probability of heads then heads. It's a nice shorthand way of writing probability. Okay, so let's make it a little bit more complicated. So if we roll 2 dice, and we want to get a sum of 7. So the probability of rolling 2 dice is getting a sum of 7. Well, there's lots of different ways to get a sum of 7. So you might not be able to do this just in your head thinking about all the possible outcomes. Possibly. Okay? But to get a sum of 7, you can roll a 6 and a 1, or a 5 and a 2, or a 4 and a 3, or a 3 and a 4. And a 3 and a 4 counts differently than a 4 and a 3. To make sure that you understand the difference, I used a red die and a white die here so that we know that a red 4 and a white 3 is different than a red 3 and a white 4. Or we could roll a 2 and a 5, or a 1 and a 6. And those are all the different ways that we could roll a 7. So there's 1, 2, 3, 4, 5, 6 of those. And out of rolling 2 dice, all the possible things that can happen in this table, there's 36. So that would be 6 out of 36. And in probability, we always want to make our reduced fraction. And if you make that reduced fraction, that would be 1 out of 6. In this lesson, we also want to change those into percents because I want you to express your probabilities in fractions and percents. So to change that into a percent, it's just 1 divided by 6 and then multiply by 100 to make that 16.6 repeating percent. So the probability of rolling a sum of 7 is 16.6 or 16.7%. Okay? So that's called the fundamental counting principle. And you'll notice that since each die has 6 sides, what we're really doing is multiplying 6 times 6 to get the total number of outcomes. See, the total number of outcomes for the first die is 6 total outcomes. Total outcomes for the second die is also 6. Total outcome for both dies together, 6 times 6, 36. It's very convenient that way. Hey, if you think about when we did the 2 coins, the total number of outcomes for one coin is 2. The total outcome number of outcomes for the second coin is also 2, and 2 times 2 is 4. Remember, our probability of getting heads and heads was 1 out of 4. Oh, that's the fundamental counting principle. And you could figure out the total number of outcomes without drawing, this is called the sample space, because if you can multiply them together to get the total, that would be nice. Now, to find the number of successful outcomes, like we did here, you still might want to draw it out, okay? For example, if you had 3 pairs of pants and 3 shirts to choose from, the total number of possible outfits that you could wear. Well, if the number of pants total outcomes is 3, and the number of shirts, the total outcomes is 3, that 3 times 3, that would be 9. 9 possible outfits. So just 9 possible combinations. Now, you might not know what those combinations are unless you make a diagram like this. This is a tree diagram for 3 shirts and 3 pairs of pants. Okay? But we can easily multiply them together to figure out the total number of outcomes, which is nice. So we can use the fundamental counting principle in that way, using multiplication, to do much more complex things. Now, we're not going to get into permutations and combinations in this lesson, but that would be, if you've heard of those, one thing that you could do. Well, here's an example. So in Ohio, the license plates used to be like this. They would be 3 letters followed by 3 numbers. So how many possible license plates are there? Well, each letter could be any one of 26 of the alphabet, A through Z. So in the first position, we have 26 possible things that could go there. In the second position, we also have 26 possible things that could go there. In the third position, we have 26 possible things that could go there. So to find out those totals, we would multiply, and it's going to be a big number, 26 times 26 times 26. But those are followed by 3 numbers. Well, the numbers can be any number, any digit, like from 0 to 9, and there's 10 of those. So if there's 3 digits, there would be 10 for that one, 10 for that one, and 10 for that one. To get the total number of license plates possible with that combination, 3 letters and 3 digits, we would have to multiply 26 times 26 times 26 times 10 times 10 times 10, and that would be 17,576,000. Now, I don't know what the population of Ohio is, but I think it's more than 17,576,000. That's why they had to change the way the license plates were made. But there's an application of the fundamental counting principle for a much more complex problem. And if we were finding probabilities, then sometimes we want to use it in this way. Well, we will see. Okay. Now, when we have more than one event happening, this is where the fun happens. Combination of 2 or more events. Then that's compound probability. And for compound probability, there's 2 different kinds. There's independent events and dependent events. And for independent events, you can imagine like being independent, those events independent of each other, like one does not depend on the other one. So if you toss a coin and roll a die, those are independent. The outcome of the coin does not affect the outcome of the die. Picking a card and spinning a spinner. The outcome of picking the card does not affect the spinning of the spinner. Tossing a coin and tossing the coin a second time, the second toss has no, there's no effect on that coin for the results of the first toss. Doesn't affect the second toss. Now, dependent events are then the opposite. So if you've ever tried to pick a pair of matching socks from a drawer in the dark, then that's two socks, the picking the second sock has is affected by like whatever you pick for the first sock. So if you pick a black sock out, now there's one fewer black socks in the drawer to choose from, so that affects the probability of the second choice. Okay? Or choosing a marble from a bag of colored marbles, then choosing a second marble without replacing. So that's really the key here with the dependent events is doing something, not putting it back the way it originally was before you do whatever comes next. Okay? Now, if you put it back and then choose again, those would be independent. So, on the choosing of the socks, if you put your hand in the drawer and you pull out a black sock and you're like, oh, I don't want to wear black socks, so you put that back, then the choosing the second sock would be independent of the first one. But if you don't put it back, then the second one is dependent upon the first one. Okay, we shall see. We'll do some of those. So here's some independent events. Two coins are tossed. What is the probability of both landing heads up? Now, we did this problem before, but I just want to show you another way that you could do this problem. So the first coin, all by itself, is we're going to compute the probability of getting heads. Okay? And then the second coin, all by itself, we're going to compute the probability of getting heads. So we're going to take those two events independently, separately, and then we'll see what we can do with them. Well, for each coin, the probability of getting heads on that coin alone is just 1 out of 2. The probability of getting heads on the second coin is independent of the first one, is still 1 out of 2. So we can multiply those together. And if you multiply two fractions together, you multiply the numerators, multiply the denominators. 1 times 1 is 1, 2 times 2 is 4, 1 out of 4. That's an easier way to do the problem for the two coins. See, we don't have to draw out the sample space because we can imagine in our head, because it's an easy example to figure out 4 possible outcomes, but we can just multiply two separate probabilities together to find the probability of them happening together. So it looks like this. Probability of getting heads and heads is equal to the probability of getting heads, oops, let's use parentheses there, times the probability of getting heads. Okay? Well, if two coins are tossed, what is the probability of the nickel landing heads up and the dime landing tails? Well, for the nickel to land heads up, the probability is 1 out of 2. For the dime to land tails up, the probability is 1 out of 2. So that would still be 1 out of 4. Because those are independent events. Doesn't really matter, the first one doesn't affect the second one. Okay, now this one is different, so read this one carefully. Hopefully you didn't skip ahead before you got to the third one. Oh, my goodness. Okay, two coins are tossed. What is the probability of getting at least one of the coins landing heads up? Okay, so at least one landing heads up. This is different. So I'm going to show you two different ways to do this problem. Now, we're going to have to do some counting on this one. It would be helpful so that we could see what we're counting to write down the sample space. So I'm going to make a little table. Let's go back to our table here. Remember, the first coin could either be heads or tails. Second coin could either be heads or tails. So that leaves us with this table: heads, 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 tails, tails, heads, and tails, tails. Okay, so at least one of the coins landing heads up could either be, and we're going to write this out, heads, tails, that's 1. Heads, heads, that's 2. Tails, heads, that's 3. So if you just count them this way, then you can see that that's, 3 out of 4. Okay? Now, if you listed them, let's say in your head, then you would say, well, it could be heads, heads, because that's at least one heads up. And that we know is 1 out of 4 because we did it earlier. Or, I'm going to write the word or in there. Could be the heads, tails, because that would be 1 heads. That's also 1 out of 4. See, we can tell on our table over here, heads, tails. There's one of those out of 4. Or it could be tails, heads. And that could be 1 out of 4. And now look what happens here. We have 1/4 plus 1/4 plus 1/4 is 3/4. So in this case, we're taking those 3 separate probabilities and adding them together because we're not trying to find out, like in the first one, heads and heads. We're trying to find out heads, heads, or heads, tails, or tails, heads. So when we say or, we're counting more of them. So it's like the 2 dice. When you could roll a sum of 7 by rolling a 6 and a 1, or a 5 and a 2, or a 4 and a 3. See, we counted all of those. It's like adding them all together. See, with a dice problem, it could have been for a 6 and a 1, 1 out of 36. For a 5 and a 2, 1 out of 36. For a 4 and a 3, 1 out of 36. And if we add those together, 1 out of 36 plus 1 out of 36 plus 1 out of 36 plus another 1 out of 36 plus 1 out of 36 plus 1 out of 36, that's 6 out of 36. Keep in mind when you add fractions together, the denominator stays the same. You need a common denominator, and it does stay the same when you add them together, like 1/4 plus 1/4 plus 1/4 is 3/4. Okay, so when you're counting, keep in mind how the problem is worded, because sometimes it will be and for 2 events happening together. Sometimes it'll be or. Can we get this or that? So be careful about those. Okay, so to win a dice game, you need to roll a sum of 7 or a sum of 11. Okay, so we need to count the probability of getting a 7. Okay, so let's see that. So we did this earlier, remember? 1, 2, 3, 4, 5, 6. There was 6 out of 36. Now, we want to reduce it, but I'm going to not reduce it yet. I'm just going to leave it 6 out of 36. Now, it says or, this is important, a sum of 11. So we need the probability of getting an 11. Oops, I put an H on there instead because I was thinking heads and tails. Oops. 11. And let's see, we can get 11 by rolling a 6 and a 5 or a 5 and a 6. So there's 2 ways to get an 11 out of 36. 2 out of 36. And since it's or, then we're going to add those together, and that would be 8 out of 36. Now, if you think about it, it makes sense, because what you're doing, if you are going to win, is you're going to count all of the ways that you can win. Right? Count all the ways you can win. So you can win with a 6 and a 1, or a 5 and a 2, or a 4 and a 3, or a 3 and a 4, or a 2 and a 5, or a 1 and a 6, or a 6 and a 5, or a 5 and a 6. And if you count all of those, there's 8. So that's what we're doing when we're adding them together. We're just counting more. So 8 out of 36. Let's write that as a reduced fraction. So what goes into both 8 and 36? I believe 4 does. So that would be 2/9. Let's write that as a percent. So 2 divided by 9 is 0.2 repeating. Multiplied by 100 is 22.2 repeating percent. So on your assignment, I want you to write the reduced fraction and the percent for all the probabilities that we find, just for nice percent practice. Okay. Now, for dependent events, you have to be careful about counting. Okay, so in this jar of colored marbles, what's the probability of choosing a green marble? So we're going to choose a green one. Then after not replacing the first marble, choosing a second marble that is also green. Okay, so we do have two events going on here. We're choosing a first marble and then we're choosing a second marble. Keep in mind that we said we're choosing a first marble and then we're choosing a second marble. That's important. So let's find the probability of getting the first marble to be green. Now, when you do probabilities, especially dependent events, you have to make some assumptions. We're assuming for the second marble that we were successful on the first one. Okay, because that's the only probability we're interested in, is choosing a green followed by another green. Okay, now I've already counted all the marbles here. There was 10 green ones, 7 red, and 3 blue. That makes a total of 20 total. So the probability of getting a green one would be, I'm going to leave it in non-reduced form first, okay? So there's 10 out of 20. Okay, now we're going to choose a second marble that is also green after not replacing the first one. So if we don't replace the first one, okay, so I'm going to take one of these green marbles out. Okay, took a green marble out. Now how many total marbles are green in there? 9. Right, so we still have 7 red ones and 3 blue ones because we didn't choose those. What's the total now? 19. Okay, so for the second green one, that's going to be 9 out of 19. So that's why this is a dependent event, because we didn't put the first one back, and it changes the totals, total of green marbles and the total number of marbles. But we still want to find the probability of these two events happening together. So we're picking the first one to be green and the second one to be green, so we are multiplying those. Now, the reason I didn't reduce them yet is because I wanted you to see how the numbers are changing. It would really be easier if we were going to get a reduced fraction to reduce before multiplying. Okay, but just for a fact, I'm not going to do that. I'm going to take 10 times 9, which is 90. 20 times 19, which is 380. And then we could reduce that fraction, which I believe is going to be 9 out of 38. Yeah, I don't think it reduces more than that. Okay. If we're going to write that as a percent, it's just 9 divided by 38, multiplied by 100, 23.68, 23.7 approximately. Let's round our percents to the nearest tenth. 23.7%. Okay, so that's a dependent event. So you have to recount because the numbers change. All right, let's try the second one. What is the probability of choosing a green marble, then, after not replacing it, choose a second marble that is blue? Okay, so we want to choose a green marble. And then, after not replacing it, we want to choose a blue marble. Okay, so put the jar back in its original configuration. Okay, so that there are 10 green and 20 marbles altogether. So that's 10 out of 20. Now, we don't replace the green one. So you have to assume, okay, we got a green one. We're not putting it back. Now we're going to choose a blue one. Well, because we didn't put back the green one, we still have 3 blue ones. So that number didn't change. But there's still, the total number is reduced because we didn't put the first green one back, so it's 19. So sometimes you have to reduce everything, sometimes you don't. It just depends on what your goal is for the probability. So in this case, we would multiply those together just like before, because we were trying to choose a green one and then the blue one and the blue one. We were multiplying. So 10 times 3, 30, over 20 times 19, 380, which is 3 over 38. That should be 7.9%, approximately. Approximately 7.9%. Okay, questions on that? You have to recount the totals. Sometimes you have to recount the number of marbles that you're choosing and the total. So be sure you reduce those for dependent events. Pay attention to whether or not you are replacing, not replacing, or replacing. Okay, so let's try this one. So in this jar, colored marbles, what is the probability of choosing 2 marbles that are matching color? Oh my gosh, this is going to be harder now. So to get a matching color, we can either get green, green. Now, if we're getting a matching color, it didn't say so on here, but assume that we're keeping them. Like if we choose a green one, then we're going to keep it and then try to get another green one, right? Okay. So green, green. What else could happen to get a matching color? Oh, what if we pull out a red one first? Well, then we want to get another red one, right? So green, green would work, or red, red would work, or blue, blue would work, and that would be a matching color. So blue, blue. Okay. So we have 3 different probabilities, but it's either this one or this one or this one. So after we find those, then we'll be adding those together. So green, green. Let's say the first green one would be like 10 out of 20. The second green one, remember we're keeping it because we're trying to get 2 outs that match. The second one would be 9 out of 19. Okay, we'll multiply those together later. Red, red, the first one. So now this red, red is a totally separate event from the green, green. Okay, so we're assuming now that we're back to normal and we're choosing a marble and we're finding the probability that it's going to be red. So it'd be 7 out of 20. Then if we get a red one, we're going to try to choose the second one to be the same color. So there's 6 red ones left and there's 19 marbles. Okay, or we could get a blue, blue. The probability of getting the first one to be blue would be 3 out of 20, and the second one to be blue would be 2 out of 19. Look, all of our denominators are the same. So one reason why I won't reduce the fractions first is because at the end of the multiplication, we are going to be adding, and since we're going to be adding, I do need a common denominator, and if I reduce them, I will not get a common denominator. I'll have to go back and get a common denominator. But if I don't reduce them first, then I will have a common denominator. All right? All the denominators are 20 times 19, which is 380. Okay, 10 times 9, 90. All right, 7 times 6, 42. And 3 times 2, 6. So now I can add 90 plus 42 plus 6. So that's going to be a 48, 90, 138. So that would be 138 out of 380. Because I could either get a green, green, or a red, red, or a blue, blue. So because of counting all of them, I'm counting all the green, greens, counting all the red, reds, counting all the blue, blues. I'm really adding them together to get 138 out of 380. Oh. Reducing that, and as a percent, 138 out of 380. So that reduced fraction is 69 out of 190. Apparently it's only divisible by 2. And then as a percent, that's going to be about 36.3%. There you go. That was fun. All right, so let's take a look at this. So a class has 4 girls and 8 boys. The teacher wants to select 3 students at random to make presentations on the first day of presentations. Okay, sounds reasonable. What is the probability that a girl will be the first to present? Oh, okay, so in this case, it's a simple probability, because to be chosen first, then we just have to count that one event. First chosen. Well, there's 12 total students. Oh, I'm going to write it like this. Probability of choosing a girl first. There's 12 total students to choose from, and the 4 of them are girls. So that would be 4/12, which is 1/3, which is 33.33%. Okay, probability that a girl will be chosen first, that was pretty simple, 33.33%. Okay, now, on the second question, what's the probability that at least, oh no, here we go again. At least one girl will be chosen to present on the first day. Well, the first day, you have 3 students chosen at random to present on the first day. Okay? So if the girl's going to be on the first day, then you have to write down, okay, what are all the possible ways that you could choose 3 students, one of them being a girl? Okay? At least one being a girl. Oh my gosh, this is going to be difficult. Because if you write down everything that could happen, then at least one of them being a girl could be a boy, and then another boy, and then a girl. That would be at least one girl. Or it could be a boy, then a girl, then a boy. And see, then we'd have to find that probability. Or it could be a girl, then a boy, then a boy. Keep in mind that this is going to be a dependent event, because once one student is chosen, they won't get chosen again, because they're kind of like the marble that didn't get replaced into the jar. So you don't put their name back in the hopper. Now, at least one girl doesn't mean there can't be 2. So you could choose a boy and 2 girls. And if you did, it could be the boy, girl, girl, or a girl, then a boy, then a girl, or a girl, then a girl, and a boy. See, these are all the possible things that could happen. Or at least one girl does not exclude the possibility that they all 3 could be girls. All right. So we would have to find all of those individual probabilities, similar to when we found like the marbles, and then like multiply to find that total probability, right? And the next one, and the next one, and the next one, and then add all of those together. But that seems really complicated and a lot of work. So we're going to take an alternate approach. What is the opposite thing that could happen of choosing at least one girl? The opposite thing. Why do I want to know the opposite thing? Because that's going to make our calculation a little bit easier. The only way to not choose one girl is to choose all 3 boys. All 3. I'm going to have to work on my writing here. I should just fix that. All 3 boys. So that would be the probability of getting a boy, followed by another boy, followed by another boy. Why do we want to do that? Well, there's only two things that can happen in the first day's presentations. Either they're all going to be boys or they're not. If they're not, then one of them is a girl. So we can do these as complementary events. We can find the probability of all boys and then just subtract that from 100%. All right, so let's do this. So the probability of the first one being a boy, let's see, 8 out of 12. The second one being a boy, keep in mind we reduced the total number of students and the number of boys, so it's going to be 7 out of 11. The probability of the third one being a boy, reduced again, so that's going to be 6 out of 10. Multiply all those together. 8 times 7 times 6 is 336. 12 times 11 times 10, that should be 1,320. I'm going to just multiply and check that. 1,320. Okay. Now, remember what we're looking for is at least one girl, which is the opposite of all three boys. So all we have to do is take one. Okay, so for at least one girl, one minus 336 over 1320. Keep in mind that 1 is 1320 over 1320. And 1320 minus 336 is 984. So that should be 984 over 1320. Fantastic. As a reduced fraction, that would be 41 out of 55. As a percent, that's going to be 74.5%. So, in this case, we made good use of our complementary event. At least one girl, and that was so much easier to calculate that way than it would have been to do all of these. Wow. So you kind of want to pay attention to all of the things that can happen. And if it seems really complicated, try going at it from the opposite direction. Sometimes you'll find out that you can surprise yourself and make a way easier calculation. Because I didn't want to multiply and add all those together. That's way too hard. Okay, let's try this. We have a table like this, and in this table we want to find certain probabilities. I think we can do it. Since we have a table, we have all the numbers that we need, but reading carefully is important. So let's do this. So here we have a table of all the students living on campus and off campus, and students who have a part-time job and no part-time job. And there's a total of 10,000 students. That number is really convenient. That's nice. What is the probability that a student chosen at random? So now, if we're choosing a student at random, we're choosing them from the total. 10,000 students. If you're choosing a student at random who lives on campus, probability that they live on campus. Okay. Living on campus would be 4,000 total out of 10,000. So that would be 4 out of 10, or 2 out of 5, or 40%. Oh. So if we choose any student at random, walking across the green, and we say, hey, do you live on campus? 40% of the time, the answer would be yes. Okay, let's try question 2. What is the probability that a student who lives on campus has a part-time job? Okay, now we're not choosing all students this time. We're choosing students who live on campus. We want the probability that a student who lives on campus. Okay, so lives on campus. So now 4,000 is our total. So out of all the students who live on campus, what is the probability that they have a part-time job? So part-time job, that would be 1,000. So that'd be 1/4, 25%. So you have to be careful about not always choosing. See, we didn't choose 10,000 for our total number of students that time because we are only finding the probability that they have a part-time job if they live on campus. So you have to be careful where you get your totals from. Do not always use the biggest number for the total. All right, let's go to the third one. What is the probability that a student who has a part-time job lives on campus? Wait a minute, isn't this like the last problem? The last problem was, what is the probability that a student who lives on campus has a part-time job? This one is, what is the probability that a student who has a part-time job lives on campus? Okay, so now we need all the students who have a part-time job. That's our total. Have a part-time job, that's 5,000. Then they live on campus. Okay, out of those 5,000 who have a part-time job, they live on campus. 1,000. So that's 1/5. Oh, see, this is different. So that made a difference. That's 20%. The way the problem is worded is important. So the probability that a student who lives on campus has a part-time job is different from the probability that a student who has a part-time job lives on campus, because that changes the total. All right, let's try this last one. What is the probability that a student either has a part-time job or lives off campus? Okay, so either or. Either has a part-time job or lives off campus. Okay, now what's the total that we're dealing with here on this one? The probability that a student... Now, it doesn't say a student who, right? Like number 2 and 3 did. A student who lives on campus, a student who has a part-time job. It's just a probability that a student either has. Okay, so this total is going to be out of our 10,000. Okay. So either has a part-time job. Okay, let's find all those. Has a part-time job. That would be 5,000. Okay, those are the part-time job ones. Or lives off campus. All right, so or, remember or? Plus lives off campus. So lives off campus. Now there's 6,000 total that live off campus. But some of those, I think we are already counting in the part-time job. I don't think we want to count them twice. Either has a part-time job or lives off campus. Because if we did that, the probability would be greater than 100%. Because if I put 6,000 over 10,000 plus 5,000 over 10,000, that's going to be 11,000 over 10,000. That means the probability the student either has a part-time job or lives off campus would be 110%. And that's not possible. Okay. So we have to make sure we don't count them twice. So we have either a part-time job, we have that one, 5,000, or lives off campus. So the living off campus, I'm going to use the 2,000 students here because we've already counted these. We've already counted those because these 4,000 students, they're already in here. Already in there. So that would be plus 2,000 over 10,000. So you really have to be careful about reading into the problem, not counting things more often than they really need to be counted, and make sure your answer makes sense, because when we add these together and we get 7,000 over 10,000, which is 7/10, which is 70%. Oh. That would make sense. Okay, But if you weren't paying attention and you put 6,000 over 10,000, and then you add them together and you got 11,000 over 10,000, and you got 110%, then you should realize that how can the probability the student either has a part-time job or lives off campus is going to be 110%? It's not possible for any probability to be over 100%. Okay? And surely there are some students that have neither a part-time job nor live off campus, so the probability that they do has to be less than 100%. So just keep all those things in mind. Good luck with your probabilities. I think it's kind of a lot of fun, and we'll see you the next time.